Okay, hello everyone. My name is Angela Jimenez, and this is Pedro Acevedo, and today we're going to present Virtual Rooming, immersive layout co-design with a virtual agent. This was my master thesis at Purdue University.
VR has been used for 3D shape and object edition for 3D modeling, as well for collaboration with embodied AI agents for different tasks, as can be, for example, puzzle solving tasks. And there is another direction combining these two principles in which user and agents co-design in a creative task, such as editing the appearance of these objects. However, we have noticed a gap in this. There's few research in this kind of AI collaboration with open-ended designs. That's why we look at VR layout design. Here, user and agent work together to arrange furniture items in a space. The key point here is that there is no single correct answer. Multiple arrangement can work. This is differently from other tasks. For example, in the puzzle solving, there is only one solution. In this kind of task, we also want to explore how user experience change depending on the AI strategy during this co-design. We choose the layout design because it's a well-studied area in computer graphics and with multiple optimization generation optimization methods. Previous research used algorithms and pattern finding techniques to support people in designing layouts. Our project builds on this idea, focusing on how human and AI can collaborate in this creative and open-ended design task. That's why we have proposed the following co-design system pipeline. In this pipeline, we have the virtual environment. In this virtual environment, we have two areas, one inner and outer area, in which user and agent will be placing items to design a living room layout. We also have a data set of furniture items. These have been taken for previous research. In here, these items can have some sort of relationship in terms of dominant and subordinate. And also, the dominant objects are able to determine the ideal relative position, rotation, and distance of the subordinate items. We also have, obviously, a virtual agent. In this case, this is an A-star agent, driving agent for navigation and to avoid obstacles. As well, it has two states, placing objects. The agent takes one of the furniture items and places it in the living room. And then we have the waiting state. So once the agent is done placing, it will be back to our initial position. And as well, this agent supports different co-design strategies. In terms of these co-design strategies, we have the agent brain for decision making. Specifically, we define three concerns. First, we have the boundary concerns. In this, we're considering the distance between the items and the wall, as well as rotation. We also don't want the objects to collide with each other, as we want to do a good design, as well as the pairwise relationship with these objects. So dominant and subordinate relationship will have a crucial role in this course. Finally, during this optimization method, the algorithm considers multiple placement options and applies a greedy-based method to find the optimal solution. The optimal solution will be an ideal position and rotation of a selected item. This approach minimizes computational costs for real-time interaction while maintaining coherence with user decisions. Finally, we have the turn-based interaction approach. In this case, user places item in the living room, as well as the agent after it. In a turn-based approach, user is able to add items as well as make corrections. That means that the user is able to edit objects that are already placed in the layout, but differently, the agent is not able to do that. It's only able to add items, as you can see in this video. That's our co-design system pipeline.
Okay, now going for the research questions, we have 5 main research questions, and we basically want to see how the virtual agent co-design strategy impacts the agent perception, agent's awareness attribution, user experience, design satisfaction, and user activity. So we have 3 main co-design strategies. The first one is random, where the agent places the items based on a random position and rotation. We have also a template where we use a predefined layout to place the items in the environment. And we have an optimization algorithm, which is the one we're presenting right now, where we consider the objects in the environment to make the decision-making process of the agent. This is a short video of how the agent will place the items around the environment, and that's the final layout of each of the co-design strategies if it was only the agent placing the objects. So for the methodology, we have 14 self-reported variables and 4 in-game measurements. We recruited 24 participants, 13 male and 11 females. So for agent perception, we found significance in co-presence, perceived collaboration, trust, and performance. For co-presence, optimist-based co-design strategy was higher than random. Perceived collaboration, optimist-based was higher than template, which was also higher than random. And for trust and performance, optimist-based and template were higher than random. This is because adaptive behavior enhanced collaboration quality and trust by demonstrating intentional design reasoning. So for agents awareness attribution, we had 3 variables. All of them were significant. For private awareness and for public awareness, optimization was higher than template, which was also higher than random. And for surrounding awareness, optimization and template were higher than random. This could be due to the adaptability of the optimization-based condition. So the algorithm considers the environment and therefore the previous decisions of the user. And then we have user experience. We had 5 variables, all of them significant. For task load, optimization was lower than random. For system usability, optimization was higher than random. For enjoyment, optimization and template were higher than random. And for feature interaction, optimization and template were also higher than random. So structured predictable agent behavior reduces cognitive load and increases enjoyment. And then for design satisfaction, we had 1 variable. We basically just asked them how they felt with their result design. And both optimization and template were higher than random. And basically, the algorithm and defined approaches produce significantly more satisfaction than random design. And then we have the user activity. We had 4 in-game measurements. We find significance in 3 of them. So we find significance in items placed by user. This is related to the items the user brings to the scene. This is significant because significantly higher optimization and template to random. So the user placed more items in these 2 scenarios. We had also corrections. So all the modifications the user did to the objects that were placed in the environment already. The random scenario was significantly higher than the optimization, so there were more corrections there. And we have also corrections that were by the items placed by the agent. So the user modified all the items placed by the agent, and the random was significantly higher than the optimization and template. This makes sense because adaptive behavior encourages more active user participation and reduces significantly the corrections. And then we had an open-ended question. We asked how was the experience, and most of the users demonstrated, let us know that it was a fun experience and that they could distinguish different awareness for the agents, and that it would be nice to have more communication with the agent besides just placing the items. So for our takeaways, we have that participants reported higher perceived collaboration, trust, and co-presence with the optimization-based algorithm agent collaboration. And we also have that adaptive behavior creates stronger impressions and awareness of awareness and intentionality. And the approach of optimization, the optimization-based approach reduces cognitive workload while increasing enjoyment. And this is also backed by our behavioral data and the quality feedback we got from the questionnaire. So for our future work, we want to take a deeper look on the goals of the users, more over like we right now just take into consideration in our algorithm the current layout design. We want to go further. We want to look what is the intention of the users by placing objects. We want to try different views, maybe God view, maybe give more control to the users of like the whole environment, and try different environments, not just like a living room, but other places. And we want to modify the algorithm to try improve it and make it more like probably communicative, or also try some other techniques like reinforcement learning. And that's all. Thank you.
Time for maybe 1 or 2 short questions from the audience. Anybody? Yes, please.
So I can imagine that you, thank you. Interior design and architecture are expertises. So I can imagine that you take these expertises into account when you take it to the next level. Is that one of your goals?
Initially, we consider like previous research for like the decision-making process of like the placing of the objects. If we look into like the expertise of what goes down to what is like an architecture's job, I would say it's more like trying to make the collaboration better, more than like going deep on the topic of the collaboration kind of situation. I don't know if you want to say something.
I mean, that will be a next step, because in this paper, we wanted to see how this collaboration happens more than the quality of the design itself. But that will be an ideal step on this paper for sure.
Thank you.
I have one question. So you compared 3 conditions, random, template, and optimization. I was wondering if you have any findings about when not using a human-like virtual agent, so everything's just placed automatically?
So that's a really good question. We did like on our previous like references, we have some projects that use like that comparison. So let me show you. Where is it? Rush. Let me just find it. So Rush et al. In 2025, they basically did that. They compared a embodiment into different experiences for designing, and we just wanted to go deeper on the embodiment, like what happens if we have like a body and a face to that AI. So yeah.
Yeah, basically the research is what your question is, and they found that the preference over embodied agents in this case.
Okay, thank you very much again.
Hello. Okay, so before I present, Jingjing requests me to take a selfie with everyone. So she just wants to know how many people attend her talk. Right, so I'm presenting on behalf of Jingjing and the team. So unfortunately, she cannot be here presenting her own work. So at ISMAR, myself, Tam, and Ganli are present. So happy to talk to you after the session. Right, so hat swapping. So this research is based on 2 foundational pillars. The first is immersive VR, which provides a shared spatial world and a crucial sense of embodiment. The second is capable AI, which move agents beyond just simply tools and into a role of active teammates. The combination creates effective human-agent team hat, where a shared goal is achieved through collaboration. This setup allows us to tackle a central question in dynamic hat. How can embodied virtual agent, EVA, best function as a substitute for human instructor, for example, who might be temporarily unavailable in virtual training session, for example. So this concept has its foundation in like 2 decades ago with the idea of hybrid agent, a single virtual character capable of seamlessly switching between human and AI control to maintain what was termed continuous presence. Building on this, our team proposed the virtual triplets concept, envisioning dynamic AI stand-ins that could help one instructor manage multiple simultaneous training sessions in immersive VR. Most recently, perceptual studies such as the Details paper have shown that the design of such agents is far from trivial. Using a result of our study, they demonstrated that appearance matters. Visually, similar agents can significantly enhance user trust and presence in online meetings. So now, when we bring together the concept, right, our envisioned applications, the growing evidence that the appearance truly matters, clear and underexplored research gap emerged. We know the concept is feasible, and we know appearance influences perception, but what remains unknown is how to design the agent's visual appearance specifically for the dynamic back and forth role transitions that are unique to immersive training environment. Should the agent appear as an identical clone or of the instructor, creating a seamless visual handover, or should it look completely different, making the change obvious? So this wasn't just a minor design detail, it represented a fundamental choice that could dramatically shape the user experience and interaction patterns. And this became the central question of this research. So the dilemma led us to formulating these 3 research questions. First, on performance, how does the agent's presence affect efficiency and workload? Second, on perception, how does the choice between a shared versus unique appearance influence user preference? And finally, on interaction dynamic, do people actually change their communication style when switching between human and agent instructor? So to investigate this trade-off between continuity and clarity, we designed hat swapping experiment. We wanted to compare these 2 opposing design philosophies against a control baseline. So we have shared appearance as a condition where agent that substitute the instructor is visual clone and speak with the instructor's clone voice. On the other hand, you have unique appearance condition where the agent has a clearly distinct look and voice. And then we have a baseline where there's no agent and the participant work independently on their task. So to execute this control comparison, we first had to develop a hat swapping system. There is our custom experimental platform built on Unreal Engine. It functions as a collaborative VR environment, a shared virtual kitchen where a student receives instruction. The system's most critically, the critical feature is its ability to manage dynamic role transition. When the human instructor steps away, the system automatically triggers an EVA to substitute taking the instructor's place. And crucially, the system is fully configurable. It allows us to implement both visual changes and voice cloning, giving the precise control needed to create our shared appearance and unique appearance conditions. Right. So we conducted a within subject user study with 21 participants to ensure consistency and control performance variation. The instructor role was performed by 3 trained actors, each with their own unique realistic avatar to represent them. For the task, participants prepare a dish following a recipe in the virtual kitchen, requiring them to find ingredients and use tools, encouraging reliance on guidance. So within each of the three conditions, the instructor would temporarily leave and return 4 times. We use a mix of informed and uninformed transition, informed being verbally announced and uninformed being silent swapped to observe more natural adaptation. To evaluate, we use a mixed method approach. This includes objective data such as task completion time and chat log, alongside subjective questionnaires, including workload comparisons, preference ranking, and finally, the interview. So first, in terms of the results, the data confirmed the value of having the EVA stand-in approach for maintaining the momentum of the learning. Across both agent conditions, SA and UA, participants experience a statistically significant reduction in task completion time compared to no agent condition. Subjectively, the presence of EVA also significantly alleviated the perceived task load, reducing temporal and physical demand and frustration. And so this have established a strong baseline. Using an EVA stand-in is a highly effective strategy for ensuring task efficiency and continuous support in virtual training. When we asked participants which agent condition they prefer most, the results were interesting. While the majority rejected the no agent condition, there was no significant difference in preference between share and unique appearance. There was no single best design. And so to understand this better, we dive deeper into the feedback and interview. The interviews reveal why the preference were split. It all comes down to a core trade-off between experiential continuity and role clarity. Users who prefer the shared appearance value the seamlessness and sense of continuity, which genuinely foster trust and rapport. In contrast, unique appearance value, people who prefer unique appearance value the absolute transparency of knowing they were talking to an AI. This reduces potentially confusion and lower the perceived social burden of interaction. So each approach has downsides, where SA risks inducing uncanny valley, while UA was sometimes perceived as jarring or inconsistent during role transitions. Finally, analyzing chat logs and observations reveal a fundamental shift in interaction dynamics. With the human instructor, communication was rational. Participants sought feedback and validation, asking, for example, am I doing this right? The moment AI agent took over, more directive dynamic emerged. Queries become more concise, task-focused commands, treating EVA as an efficient assistant. This held true for both SA and UA conditions, suggesting appearance had limited impact on direct communication style with the AI. However, appearance did impact transition awareness. The unique agent made the switch obvious. The share agent often masked the role switch, leading some participants to inappropriately carry over their command-like style with the human instructor return. So what does this mean for designer of a human agent system? Our findings suggest 3 key design takeaways. First, choose appearance intentionally. If your goal is trust and rapport, such as therapy or coaching, use shared appearance. For clear role distinction in high stakes or technical tasks, use unique appearance. Second, smooth transition is important. Soften the downside of each approach with subtle cues. For example, for shared agents, reduce ambiguity with dynamic name tags or visual markers showing AI control. For unique agents, ease transition with smooth animation, such as the agent walking into the view. And finally, third, match tasks to user expectations. Users prefer giving direct commands to AIs, seeking nuanced feedback from humans. Design system accordingly, use AI for consistent factual delivery and humans for adaptive feedback and rapport building. Right. Finally, we acknowledge 3 key limitations that shape the next steps in our research. First, gender confound. Our design unintentionally link visual uniqueness with the agent's gender, making it unclear whether preference were driven by appearance or social cues. Next, trained actors. Using trained actors ensure consistency but limited insight into authentic instructor-student dynamics. And finally, simplified interaction. We examine only one-to-one swaps and did not include triadic interaction among human, agent, and student. Right, hopefully that's on time.
Thank you very much. Tom? One or two short questions. If you have questions, please come up to the microphone podium. There are two of them.
If you have
in the middle
anything
of the-
technical, you can email Jing. So that's all I can say.
Any questions? Well, in the meantime, I'll have what I wanted to know was, did you compare, for example, I guess this situation is when the instructor is not available, you're replacing it with an avatar, either a unique or the shared one. Was there any comparison between when the instructor was available and when he was replaced with the avatar? What the users found the avatar to be odd or strange or anything like that?
Right. So that's exactly one of the limitations we want to address, and actually we are actually addressing in the current iteration of the research, where all of the options present and what are the actual roles that they should be playing. And again, we believe in human-led learning, teaching learning. As a professor myself, I still do have bias and think that you can't replace professors easily. Hopefully. And so that is also with the current AI capability, it cannot provide that nuance yet. In the future, it probably can. And so eventually more roles and more capability of AI will emerge and can replace certain, I guess, capabilities that human kind of like used to have advantage of. I'm not sure if that answers your questions, but yeah.
Okay. Question by Doug.
Yeah. Hey, thanks for your talk. So I just wanted to ask, how intelligent was the virtual agent? So
Right.
was the agent unable to answer questions like, "Am I chopping this right?" Or did the agent just give similar answers to what the human would give?
Thank you, Doug, for the question. It's quite important to actually talk about the capability. Right now, we try to constrain the capability of the agent to just a task specific. So we do provide encoding of current setup. For example, what the student have done, where things are at, and we encode that to provide into the prompt along with conversational information, so they have some awareness, spatial awareness of the environment and the student progress, for example. In terms of capability, as we all know, large language models such as GPT 4.1 has some reasoning, right? Has some kind of like acceptable reasoning, and they're capable of actually providing good enough information and guidance, especially if we do provide prompt instruction in the beginning and provide some background information for it to process. Again, it doesn't have the visual awareness directly from the environment, and we have to manually provide the encoding. But again, as you know, the vision action model, vision language model, becoming more reliable. Hopefully, maybe in the future, just like in robotics, it can reason and actually have their own perception of the visual information by themselves instead of having to do manual encoding. Yeah.
Thank you.
Hopefully that answers your questions.
Okay, thank you. One more time.
Right, thank you.
Let's
Hi, I'm Simile Meyer. I'm from the University of Hamburg, and I'm going to present you today our work with the title Laughing Together, a pilot study on the role of virtual agents in emotional contagion, conformity, and opinion shaping in a virtual stand-up comedy club. I will talk about why it is important to consider emotions and group processes when working with virtual agents. Sorry. So when dealing with virtual agents, we must ask ourselves what unconscious influence can virtual agents have on a user? And for our study, we were interested in influence on emotion and influence on opinion. Two processes are mainly relevant here. First, emotional contagion, when a person, or in this case a virtual agent, transfers his emotion to another person, and group conformity, when group members transfer their opinion to other group members. Both processes have been studied before. For example, Tsai et al. Had shown that emotional contagion can occur through virtual agents. In this example, the participants reported a higher happiness when the virtual agent showed a smile. And group conformity virtual agent was tested too, here with a virtual experiment of Ash's line experiment. And in the study, they showed that when the virtual agent gave a wrong answer, the participants gave wrong answers too. So this means both effects can happen with virtual agent, but they were mostly studied separately. And we were interested to see how they work together. So basically, we wanted to know if a virtual agent laughs when hearing a joke, does the participant rate this joke as funny or not? And if so, is it because of emotional contagion, of group conformity, or of both? To this end, we conducted a pilot user study. The procedure was as follows. First, the participants arrived and filled out questionnaires. Then the virtual application started. Here, a virtual comedian told a joke, and agents were reacting to this with no laughing, giggling, or laughing a lot. And then the participants rated this joke on funniness on a scale from 1 to 5. We had 16 jokes in total, and while the session, the lip movement of the participants was recorded to understand if they were smiling or laughing. And afterwards, we measured their tendency to conform with the conformity scale and agreeableness scale by the Big Five inventory. And then was the end. So here you can see a clip from the participant's perspective. Unfortunately, it's in German, so not everyone will understand it. But just you know, first there is a moderation, and then you can see the stand-up comedy club, and then the comedian tells a joke, and the agents are reacting.
Heute Abend haben wir gleich 2 neue, junge Talente für euch, die die Bühne zum Beben bringen werden. Die beiden werden abwechselnd ihre neuesten Routinen zum Besten geben. Bitte begrüßen Sie mit mir das erste Talent auf der Bühne.
Kommt ein Mann zum Bäcker und sagt, ich hätte gern 99 Brötchen. Sagt die Bäckersfrau, warum nehmen Sie denn nicht 100? Sagt der Mann, um Himmels Willen, wer soll die denn alle essen?
Heute Abend haben wir gleich 2 neue, junge Talente für euch.
Yes, so I saw some of you laughing, so it works. And here you can see the sheet where the participant rated the joke afterwards. We had 20 participants, 11 female, 8 male, and 1 non-binary person, and the mean age was about 25 years. We used a 3x6 within subject design, and the number of agents ranged from 0 to 5, and each could show 3 different levels of intensity of laughter. So 0 is for no laughter, 1 is for giggling, and 2 is for a lot of laughter. This resulted in 16 trials. Sorry, here's something wrong. And this means 16 different jokes were needed. And for this, we use so-called corny jokes because they are roughly equally funny, they are easy to understand, and there's room for improvement in terms of funniness. To test this, we developed different hypotheses. Hypothesis 1A was that the perceived funniness of the joke is positively influenced by the agent's laughter. Hypothesis 1B was that the perceived funniness of the joke is negatively influenced by the lack of laughter. The next was that the influence increases with group size. For hypothesis 3, we had that the participants' laughter mediates the evaluation. And for hypothesis 4 was that participants high in social conformity and agreeableness are more affected by the agent's laughter. So let's come to the main results. This is for hypothesis 1A. So we can see here at the graph at the y-axis the funniness rating, and at the x-axis how strong the agents laughed. And when there was no laughter by the agents, the mean rating for the joke was about 2.03. And like on the right side, at the most laughing, the mean rate of funniness was 2.45. So there's a difference, and we tested if it was significant with a likelihood ratio test, and we found a significant effect. And with the cumulative linked mix model, we found that there's a significant increase in the probability of a higher rating with increased laughter intensity. So we can confirm this. Let's go to the next, hypothesis 1B. Here we didn't find any significant effects. The same for hypothesis 2. Here, 2 were no significant effects. Let's move on to hypothesis 3. It was that the participants' laughter mediates the evaluation. For this we made a mediation analysis. And what we found is that the effect of the laughter intensity on the rating is fully mediated by the lip movement of the participant. Let me break this down. So first we confirmed that stronger laughter does predict greater lip movement. And then in the second model we saw that lip movement has a strong effect on the rating, while the effect of the agent's laughter became non-significant. This means that laughter was, this means that the rating was fully mediated by the laughter of the participants. So we can confirm hypothesis 3. Let's look at hypothesis 4. Here we found a significant interaction between the laughter intensity and the conformity of the participants. And the cumulative linked mix model showed that there's a significant increase in the probability of a higher rating at higher levels of conformity. We can see this here. On the y-axis is the rating, and the x-axis shows the tendency to conform. And on the far left, there is no tendency to conform and no effect on the rating based on the laughter intensity. And on the right, we can see there is an effect on the rating when people are really conform. We did the same analysis with agreeableness, but here we found no significant effect. So hypothesis 4 was to some extent confirmed, mainly a significant effect on conformity. And as we saw in hypothesis 3 that laughter was influenced by emotional contagion 2, we developed a new assumption. Assumption 1 is that social conformity moderates the mediator emotional contagion. Simply put, if I tend to conform, I'm more likely to be emotional influenced. The likelihood ratio test for this showed a significant effect on the participants' laughter. And the result of the linear mix model showed that the interaction between laughter intensity and conformity was significant, indicating that the effect of laughter intensity on lip movement was stronger for individuals who are higher in conformity scores. We can see this here. So conformity is on the x-axis, and on the y-axis we have the lip movement, and we can see that when there is no tendency to conform, so on the left side, the lip movement was not changing, but if people are really conforming, they had different lip movement based on laughter intensity. So we can also confirm assumption 1. Let's come to our limitations. We had a small sample size of only 20 participants, so there would be a bigger sample group to confirm these results. And we must consider the potentials for demand characteristics, because we had the participants were students from HCI or psychology, and it was a within subject design, so they could guess the purpose of the study, and this could influence the rating. And of course, funniness of the joke is really subjective, so yeah, there should be something that we cannot rule out that it's like confounding our results. And we had to exclude audio data because some people were talking while recording, and we couldn't use that. So let's come to the conclusion. when we go back to our first question, what influence can virtual agents have on user? Our assumption is that individual tendency for group conformity can influence emotional contagion, which can influence the opinion of the user. What does this mean? The design of virtual agent should not only consider verbal communication, but should also focus on their emotions and how their facial expressions are. Thank you very much.
Thank you very much. Any questions from the audience? Please come up to the microphone. In the meantime, I'll ask a question. So your hypothesis 1B says something about inhibition. What about the reverse? So would you say you could induce somebody to laugh even though the joke was not funny?
But I think that's like what we did, like the joke wasn't really funny, but when the agents laughed, the participants laughed too. So we had this facilitation effect.
Okay, good. So I have some chance. Anybody else? Okay, so let's thank the presenter one more time.
Okay, hello everyone. I'm Shin from Woven by Toyota from Japan, and I'm here to present you with our work in embodied ARA navigation agent, which we integrated beam data with retrieval augmented generation for language guidance. And here is a QR code that you can scan for and take a look about the demonstration of the videos and also our paper as well. So let me get started with the building information modeling. So what is building information modeling? It's a process that you can create and also manage 3D data by carrying in like semantic and also geometry data in a whole. So you can actually like retrieve the attribute given a 3D object. And so it has been considered as a promising solution for offering structured representation of both geometry and semantic metadata within the environment. And what does this mean? It's like if you use this beam, it's very good for the RAG because RAG, you know, like you need the structure output so that the LM can understand what your retrieval and what you want to do, right? And then let's take a look of this example here. This is what kind of data the beam model can actually store. So we source like the hash of the ID and also its name and some of the attribute. Like for example, if you take a look in the laptop corner, you can see the name and capacity of a room. And this information are super useful when you are doing the navigation, I think. And then let me go through the implementation on previous work. So despite these like special grounding, it's recently progressing a lot with semantic context, but still many AR navigation systems often rely on rigid input mechanism and really fall short in how users can naturally express their intended destination. So there are usually two common approaches. One is fixed command phrases. So the user must speak exact and predefined phrases. And the other one is like keyword matching. So the system usually use embedding-based matching so that you can try to do the semantic search to a target keyword. And this is acceptable in most of cases. However, adopting either these approach alone remains still limited with indirect and contextual expressions. So one of the example here in the bottom in the left is a direct query. So this is considerable be easy because the user just say, take me to the coffee shop so that we can try to search the coffee shop and buy some like NLP processing, right? And in the indirect query, this case is much more difficult because the user intention is a little bit ambiguous and also it's not too direct, right? So for example, I'm hungry, where I can get the food. So this is required reasoning before you really do the retrieval in the like database. And this is our proposed system. So we try to connect the AR agent with multiple agent RAG for Go retrieval and for navigation. So in this system, we have the integrating with being with the vector database, and we do the planning inside the beam model, and we build this on the Unity application so that we can calculate the path and render in AR. And here's a demo video, so let me play first so that we can see how the system actually looks like. Hi, can you take me to somewhere that I can get some food?
Let's head to the coffee shop nearby where you can grab some food. Follow me, and I'll guide you to the coffee shop where you can get some food. It's open from 11 a.m. to 6 p.m. We have reached the goal.
So,
Please ask me what you
so
want
probably
to
you can
ask.
observe that the interaction between agent and human is pretty native, so that it's kind of, we are conversationing, and that is due to the reason we are using a multiple agent, RG, and also the orchestration through the agentic AI. And also the query is a little bit not so straightforward, say that I'm going to get the food, can you take me to a restaurant? But just saying that I'm hungry and I need some food. And we can try to research and try to retrieve the correct destination. And here's the methodology. So in our proposed framework, we have 3 different parts. In the left-hand side is the AR visualization, rendering. And in the middle side is a multi-agent RAG for goal retrieval for the navigation. And the right-hand side is how we deal with the external database, for example, the Bing data, and also how to trigger the navigation and do the navigation through the agent. So before we go into the main part of the RAG, we first need to preprocess the BEAM data to the vector database. And how we do it is pretty straightforward. So we try to concat the information in the metadata, including the name and some of the description. For example, the name and capacity is 10. And then we try to encode this information with the sentence level transformer. And we can get it embedded into store in the vector database so that you can retrieve the corresponding destination. And then this comes to the multi-agent orchestration. So this is our first agent, which we call a tri-age agent. So it's an agent that kicking off all the orchestration and also the multi-agent flow. So this agent is designed to classify user queries to initialize all the flow. So she need to first classify the query into one of 4 categories, including like navigation, or is this question an inquiry, or just greeting, or we are chatting, or it's just an invalid input. For example, that user just not speaking correctly and we cannot processing. And then for in this work, we mainly focusing on navigation related query. So if we are detecting this is navigation related query, so we will first be extracting a structured target and will be used as a reference to decide the goal. Let's take a look of one example here. So for example, the user query is take me to the nearest meeting room after getting a coffee. So we will know there is an order of the goal, right? So the agent is expected to generate an order list of the structure output. So our agent is able to generate the correct order. So the first one is we know we first need to getting a coffee. Well, this getting a coffee is not an explicit state destination, but it's more like implicit. I'm saying that I'm going to the restaurant. So we try to make the agent try to predict this one. It's a kind of chain of thought so that the agent can actually recognize what you want to do, what's your intention. And the agent is able to extract also semantics about what is the keywords that we need to search in the database. So for example, a coffee shop, coffee, drink, and the description is to the agent, so that agent will need to know, the agent need to suggest the user to the coffee shop. And the second, the nearest meeting room, in the second case is much more simple, so it's just explicit, and then meeting room, conference room, office space. And here's the prompt that we are giving the agent, but it might be a much longer, and it's just simple say that I need to follow our instruction and also follow the JSON that we predefined, and also generate some of the keyword of semantics and that you can use for search. And then goes to the search agent here. So we adopt a 2-stage process that combines both similarity search and also the other one is second stage LLM-based candidate selection. It's more like a re-ranking in the RAG system so that you can consider multiple criteria before you deciding the final destination. So the cosine similarity is calculated by the user query semantics, the keyword that we just retrieve, and also all the entities inside the Bing, the vector database that we do the preprocessing. And then the second part is the LLM reasoning. So we try to input also the distance between the user and also the coordinate of the 3D destination. So this distance help when the LLM want to make the decision based on the distance. So for example, if the user say that, take me to the closet, maybe the very nearest toilet because I want to go to the toilet right now, then they need to consider probably distance larger than the semantics, right? So for example, in this case, we have several candidates here. So we just list up all the entities, like meeting room, there are 5 meeting room, and there's distances, and also user's position. Then we try to find the correct one. And in this case, we can also try to consider about like how to integrate like Google Meet through MCP, for example, so that you can also understand what this meeting room is really empty or not. So that is one of the considerations you can use in the agentic flow. And then finally, we have the response agent, and we will trigger the navigation here. So the response agent generally just do the response by generating human-like a response, because that is AOM, right? And then also the navigation will be triggered and rendered through the AR visualization in the right bottom corner. And then our main research question, we have several research questions actually, but this is the main research question that we are interested in. So actually we want to know which interface, either embody AR agent, ISB, and also the AR arrow, which one can best complement the intelligence and flexibility of the proposed system. Because as you know, like recently AOM and RAG is like improving a lot, but what is the interface, what's the best interface that can best make the user perceptions of the system intelligence? I think that is really matter when you design an AI agent or the entire system for using the RAG and AOM stuff. So this is our main focuses. And here is the user study results. So we do the 20 participants, and we're seeing 20 to 50 years old. And then we do Wixon sign rank test. And then there are 5 different measures here. We try to measure the perceived clarity, if the instruction is good enough for the user to follow, and also the trust, user engagement. And the fourth one is more important, is perceived agent intelligence, is how user feeling the agent is generally smart or not, or it's just stupid and not smart at all. And the final one is cognition load, how the user spend time to reason about the instruction. And our key takeaway here is the presence of an embodied agent, which equipped with voice interaction and also local motion, like avatar is moving with you, can meaningfully amplify users' perception of system intelligence. And even though the reasoning background remains the same, so what does this mean? This means that even though you are connecting to ChatGPT, but you are using AR agent, it's much smarter you will feel than just using some of the text like you are typing on smartphone, because you can talk to the agent directly and they have some local motion that corresponding to the word or sentence that they are saying. So I think this is pretty similar to the idea like X-Work, they have the avatar like talking to you, right? You might see the news as well. And then here are some of the qualitative results I want to show you. So please see the D column. So for example, if user say that I'm a newcomer, where should I go first? So the system actually can recognize like, oh, you are the first newcomer. So probably you need to go some information center so that we have beam data for the reception or the information center. So the agent is able to bring the user to the head to the counter reception for the assistance. And this is the response that the system is generating. And also the B is quite interesting. So we want to find the nearest meeting room with more than 10 seats. So those attributes is kind of integrated in the search processes so that AOM can know, oh, we need like 10 seats. So the output will not be like eight people or some. And let me just quickly go through this one. And this is how the user trajectory looking like, and also the navigation look like. So the user follows the agent like pretty goodly. So the purple one is the agent, and the blue one is the user. And then this is more demonstration videos here. But I think you can also check the website for more details one, because our time probably limited. And then I'm going through just limitation and future direction. And I think the dependency on being an IFC, which is like you need to have before you utilize this system, is actually precise but limits deployment in incomplete or outdated models, so that you need to spend time to create this being an IFC. But there do you have some alternatives. So for example, you can do the scene reconstruction, like TSDL fusion is pretty traditional method, like LiDAR scanning or learning-based method for geometry reconstruction. At the same time, you might notice there also open vocabulary detection and segmentation coming out, so that you can assign the attribute like what Bing did to the 3D environment, so that you can apply the same system if you do the alignment pretty well. And also, I think like interactive tools for annotation for the user to add some of the goals directly, manually, that would be good. And also there are some issues for spatial alignment, but I think that is more like how do the relocalization through AR. And that's all from my presentation. Thank you.
Thank you very much. Any questions? Please come to the microphone.
Yeah, I have a question. Thank you very much. Pretty impressive work. Do you plan to implement a feedback possibility for the user to or to improve the training of the agent system? Like, this information was useful, you showed me the shortest way, I got confused, or something like that?
Yeah, I do think that is a good direction because we can base on the user's response and also probably add some like this navigation is good or not, and then we can consider this when we try to do the instruction tuning for the agent. So probably that will be more fitting to the navigation purposes because this LM is more general purposes that we can use for. So I think that is a good point. Thank you.
Yeah, thank you.
Yeah, thank you very much.
Good work.
Any other question? I have a question. So to fine-tune this ChatGPT-like service with BIM data, does it have to be trained for a specific building, or you just feed it with some general BIM models and it works for, bunch of different, untrained buildings?
Yeah, I think this framework like you can directly do zero shot, which means that any of the B model can work if you have the B model because it is kind of standardized format that the attribute is defined standardized. So probably you can just directly using if you get the B model for each of the buildings. So I think this is pretty promising as a solution, especially for example in Japan. We have the building probably being constructed before the building actually constructed. So if we can get those information, then probably can do a pretty good navigation agent indoor. Yeah.
Okay. Another question, gentleman over there.
So can you give more details on how localization works? I'm guessing you said you use VPS, but I'm guessing you have to scan the building and then align that with the BIM model, etc. Is that an expensive process? Was that hard, and how did you?
Yeah. So thank you very much for the question. That is pretty important. So we are currently using the ARDK, which is VPS services from Niantic, the company that created Pokemon Go. And I think we do also try some of the deep learning approaches, but that is more expensive because you need to set up your services on the server, right? And then after you scanning the AR scan, like you see the AR anchors, we need additional, probably this one, I actually want to talk about this, but it's not time enough. So you need to manually align the AR anchors, those AR spaces into the BIM model so that you will have a transformation, rigid transformation, try to transform between two coordinate systems. And then you can render the avatar on your phone. So that is what we need to do. And this process is manual. So I think one of the future work is how to automate the registration between the BIM and AR spaces. Thank you.
Thank you.
Okay, thank you. So I think there are no more questions. So I'd like to conclude this session. I thank all the authors and